Welcome back, everyone, to this explainer. Today, we are diving into something absolutely critical for those of you in metal fabrication or industrial procurement. Listen, if you're gearing up to Source's CNC plasma table in 2026, there's really one fundamental truth you've got to wrap your head around, and that is material physics. It is literally the ultimate key to getting your equipment sourcing right.
You know, there's this old saying out there, metal is metal. Well, if you take away absolutely anything from today, please let it be this. If you are a new industrial importer, or maybe you're bringing production in-house, assuming all metal behaves exactly the same is, without a doubt, the single most dangerous mistake you can make. I know, it sounds super simple, but I promise you, this assumption will absolutely wreck your capital expenditure if you're not careful.
Okay, let's dive right into this. Here's our roadmap for today. First, we'll hit the capability trap. Number 2, the metal myth. 3, the big 3 metals. 4, machine variables. And finally, number 5, sourcing strategy. We're going to move straight from debunking some common myths right into actionable sourcing logic. All right, Section 1, the capability trap, looking specifically at rated versus maximum cut. Now, this right here is the very first major pitfall buyers face. It is just incredibly common to get completely blinded by a machine's maximum specs instead of looking at what that machine can actually output on a realistic day-to-day basis.
So, professional procurement usually categorizes thickness into 3 different tiers. Your absolute bread and butter, that's the production cut. This is a clean, consistent cut at high speeds. We're talking typically 15 to 20 inches per minute, and crucially, it does this without overheating. Make no mistake, this is what actually dictates your return on investment. Then you've got the maximum pierce cut. This one really pushes the machine's limits, usually starting from the middle of a plate. And finally, the severance cut. This is the absolute physical limit of the machine. It is incredibly slow, the edge quality is honestly pretty terrible, and you're gonna have to do some major grinding afterwards.
So here's the trap, right? Imagine your production line primarily handles half-inch mild steel day in and day out. The fatal mistake is buying a machine that's rated for a half-inch maximum capacity just to handle that daily half-inch workflow. If you do that, you end up running the machine at its absolute limit all day long, which just destroys its longevity. Your daily material simply has to fall comfortably within your machine's production cut range.
Moving on to Section 2, the metal myth, and how alloys completely change the rules. Because we really need to attack this idea that a plasma cutter treats all metals equally. It just simply doesn't.
You see, thermal conductivity and melting points vary hugely across different alloys, and these physical properties, they literally alter the rules of your standard thickness guide. It's not a one-size-fits-all deal. You can't just blindly look at a spec chart. The specific physics of the metal you're cutting fundamentally dictate what kind of equipment you actually need.
Which brings us right into Section 3, the big 3 metals, steel versus aluminum. This is where the physics really come to life, and we get to see exactly how the core differences between mild steel, stainless steel, and aluminum directly impact your factory floor.
First up on the list is mild steel, or carbon steel. Think of this as the absolute gold standard of plasma cutting. It is incredibly cooperative. It absorbs heat really well and allows for super clean, high-speed processing. Because it behaves so predictably, sourcing agents will almost always prioritize mild steel capacity when they're picking out a general-purpose table. Now, what's really interesting about this slide is when you contrast that cooperative, heat-absorbing mild steel directly with stainless steel. Because stainless is stubborn. Really stubborn. It's a poor heat conductor, which means it requires significantly more energy to cut cleanly. The heat just kind of stays localized in one spot, and that creates a massive risk of warping, especially when you're working on thinner sheets. And because of that stubborn, heat-trapping nature, stainless steel requires high-definition, or high-def plasma systems. You also need very specific gas mixes, like H35, just to prevent oxidation on the thicker sections. Honestly, if you're sourcing equipment for, say, the food service or medical industries, these upgrades aren't just nice-to-haves. They are a fundamental, non-negotiable requirement to handle stainless properly.
And then we have aluminum. If mild steel is cooperative, aluminum is hyperactive. It is highly reflective and has super rapid heat dissipation. In fact, it gets rid of heat so fast that it actually demands more raw amperage than you'd need for a piece of steel of the exact same thickness. Crazy, right? Plus, that rapid cooling often leaves hardened dross on the edge, which means way more cleanup time for your team, unless you spring for a water table.
Let's look at the hard data for a second, comparing 45 amp and 85 amp capacities across these 3 metals. Look at the 45 amp system. With that, you can comfortably handle a 1/4 inch production cut on mild steel.
But if you take that exact same 45 amps and apply it to stainless steel or aluminum, your production thickness capacity plummets down to just 3/16 of an inch. It perfectly proves the point. The exact same amperage yields totally different capabilities depending entirely on the metal you're cutting.
Okay, Section 4. Machine variables. Beyond the chart. Because these massive material differences we just talked about, they force us to look way beyond a raw thickness chart and start evaluating the machine itself to ensure the theoretical specs match real-world output.
So let's rapid fire through some non-negotiable machine factors. You've got duty cycle, gas pressure and moisture, torch height control, and consumable life. These are absolutely crucial for your success. And let me just inject a little reality check here. Moist air kills. Seriously, if your compressed air isn't perfectly dry, it will literally murder your expensive copper nozzles. You have to ensure your sourcing package includes an integrated refrigerated air dryer.
Let's zoom in on that 60% duty cycle for a moment. This is a pure procurement metric. A 60% rating basically means your machine can run safely for exactly 6 out of 10 minutes at a given amperage. So if you're a bulk buyer and you need a 100% duty cycle to prevent downtime, a 60% rating forces 4 minutes of dead rest out of every 10. You can see how that directly impacts your bottom line, right?
Finally, Section 5, Sourcing Strategy, Evaluating Suppliers. Now we're going to take all this physics and hardware knowledge we've gathered and turn it into a practical playbook for evaluating those overseas suppliers.
First thing to note, physical table size almost always correlates with the power you need to handle specific material thicknesses. Like an entry-level 4x4 or 2x2 table is usually going to be paired with a 30 to 45 amp unit, maxing out around a ½ inch. But when you step up to a heavy gantry system, that means massive scale. We're talking 200 to 400 amp high-definition power sources that are capable of 2-inch piercing. You've got to match the table footprint to the material physics. So how do we actually verify these machines? Well, here is your strict supplier verification logic. Step 1. Always ask for raw, unedited live-cut video of the machine piercing its maximum rated thickness. Do not, I repeat, do not rely on glossy, edited marketing clips. Step 2. Verify the power source brand. Getting a reputable name like Hypertherm versus some generic IGBT inverter changes the whole shebang. And Step 3. Check the nesting software compatibility. Poor software leads to messy blowouts when you're piercing thick plates. Follow this logic and you won't get duped. Just before we wrap up, I want to briefly touch on a major 2026 trend. When should you actually pivot away from plasma altogether? Well, for materials under a 1/4 inch, the fiber laser is really becoming the preferred sourcing choice because of its incredible speed and dross-free finish. But for anything over a ½ inch thick, plasma remains absolutely the most cost-effective solution out there for your capital expenditure. Which leaves us with this final, provocative question for you to consider today. Is your next plasma table properly rated for your specific material or just its marketing? I really want you to look right past that theoretical spec sheet and let actual material physics guide your sourcing decisions from here on out. Thank you so much for joining me for this explainer. Stay focused and keep learning.